Okay, talking about momentum now. What is momentum?
Mass of an object and its velocity.
That's like totally amazing. Extra credit to you. Okay, so product of the mass of the object and its velocity. So colloquially speaking, momentum is kind of a measure of how hard it is for you to stop. If you're running really fast, it's harder to stop, right? So you have more momentum. If you're kind of ambling along, it's easier to stop. Or think of this, if you had to stop an elephant that's charging towards you, or a mouse that's charging towards you, which is easier? In principle, the mouse, right? Though in reality, we'd probably all just go eek and jump on top of the table, right? I know that I would. So I'm not dissing any of you who would do that, right? And of course, you know the way to stop an elephant. No, you catch a mouse and you show it to the mouse, and the elephant gets scared and stops.
Is that really true?
Didn't you ever watch Dumbo?
That happens in Donkey Kong.
Really? Okay, I'm ignorant of that, and I have no idea whether that's the case. The odds are that's not the case. It's probably a Disney invention, assuming that Dumbo is from Disney. I don't know where Dumbo's from.
Mythbusters proved it.
I'm sorry?
Mythbusters proved that.
That
Elephants are afraid of mice.
that they are?
Uh-huh.
Mythbusters did prove that they are afraid of mice?
Yeah.
Whoa. Okay, extra credit to you if you can find that and send me an email with that, right? And you enter your extra credit into the website. Okay. Momentum, product of the mass of an object and its velocity. So if an elephant coming towards you, large mass, hard to stop. Small mass, mouse, in principle, easy to stop. Right? Mouse running towards you slowly, small momentum, easy to stop. Elephant, or let's say we got a dog coming towards you slowly and a dog coming towards you really fast. The dog that's slower, or maybe your niece or your nephew, right? Ever had that experience? You walk in the door and your niece or nephew just flings himself or herself at you, almost bowls you over, right? So the faster the kid is and the chunkier the kid, I don't mean to be politically incorrect, the harder it is, right? To catch the person and not end up falling over. So that is an illustration, if you will, of momentum. Okay, so here is a pictorial representation of momentum. Supertanker. The text tells us that the super engines of a supertanker are cut off 25 kilometers from port. That's about 15 miles-ish. About 15 miles out from, as the ship is coming in towards the ocean. According to the textbook, they switch off the engines and the ship just coasts in for 15 miles. And it's gradually slows down due to the friction between the ship and the ocean. So the momentum of this object is so large because its mass is so huge. That's why it's able to travel for that long before it stops. Think of you, on the other hand, swimming, right? As you're swimming along, if you were to stop paddling your arms and your legs, what happens? You still travel for a bit, but you don't travel very far. I'd be surprised if you would travel to the length of this room before you come to a stop, right? Because your momentum is small compared to this. So this illustrates both inertia as well as momentum. Inertia is the tendency of an object to continue moving unless it's a force, like a frictional force, that slows it down. Okay, next slide. Impulse. Impulse is where you happen to go to a store and you see a Coach purse for, I have no idea how much they cost, $1,000, and you say, hey, I have a credit card, and I put it down and get the Coach purse. That's impulse. And of course, if you're a guy, then you get a man purse or whatever the equivalent is, right? Or a man bag. I don't know what
Satchel.
Satchel. Oh, is that what it's called? Okay, right. I have never had the experience of buying either a purse. Is that true? Okay. I've never had the experience of buying a Coach purse or a man bag or a satchel, right? So I don't know. I bought okay, whatever that is, backpacks. Okay. So impulse. In physics, impulse is the product of the force acting on the object and the time during which it acts. So think of the kid who's coming, your niece or your nephew, right? You open the door, you're visiting your sister or your brother, and the kid comes flinging herself at you, right? So what do? You brace yourself. You brace yourself, and what you do is you gently apply a force on the kid to slow the kid down, because otherwise you're all both going to end up on the floor, right? So you apply a force for a certain length of time, and that slows down the kid's momentum and brings the kid to a stop. Yes? So that is an illustration of impulse. Now, if the kid is traveling really fast, you would have to apply a greater force or apply a given force over a greater length of time. Force multiplied by the time is the impulse. So here's an illustration of a truck that's out of control. It's just like its brakes are off, and it's traveling with a high velocity. Little mass multiplied by high velocity, right? Big V, runs into this stack of like hay. What happens is, because the truck is traveling through the hay. Okay, let's look at these two illustrations. If you happen to be the driver of this truck, pickup, whatever. If you had a choice between running into a haystack or running into a concrete wall, which would you choose? Haystack. Is there anyone who would pick the concrete wall? Who spoke up? Extra credit. Okay, because I can hear a voice, but I don't know where it came from. Right. So, intuitive. Is anyone who would pick this, the wall? You all intuitively know to pick the haystack. There's a good chance if you were to do this that you will not collect any insurance money.
Your family might.
Your family might, right? Yes. So intuitively, you know your physics. You would choose the haystack. Now, the physics reason why that works is because it takes longer for the truck or the pickup to interact with the haystack and get slowed down. So the time is large. So a small force is needed to stop the momentum of the truck. So what happens is, the impulse that we saw on the previous slide, force multiplied by time, is equal to the change in momentum. Mass multiplied by velocity is momentum. Delta applied on this is change in momentum. So change in momentum is equal to force multiplied by time. So to drop the momentum of this object down to 0, I have to apply a force multiplied by time that's equal to that change in momentum. mv minus 0 should be equal to f multiplied by t. If I take a long time to apply this force, I can apply a low force. So big T for big time, small force is all that's needed. However, if you were to run into a concrete wall with the same initial momentum of the truck, what happens is now the time of interaction is very, very small because the concrete wall doesn't have any give, right? So very small time of interaction, little t, compared to the large T with the haystack, which means the force has to be very large to eat up this momentum, which means you have a very large force and you're probably dead. So don't do that experiment. So here's the relationship between impulse and momentum. Impulse is force multiplied by time. That should be equal to the change in momentum of the object that's being impacted by the impulse. Change delta multiplied by delta applied to mv. And how you read this is mass multiplied by velocity, the final mass velocity product minus the initial mass velocity product, right? That's what the delta means. Okay, so here's an application of this. Do not do this experiment. You happen to be at a bar and you had just a little bit too much, and so you see this 400-pound guy sitting next to you who comes along, and you think, hey, I can diss him. I can take him on, right? So you diss him. And what does he do? He flings a punch in your direction. If that were to be the case, is it better for you to be going into the punch or away from it? Away, right? So again, here's an illustration where you already know your physics. You know that if somebody's going to hit you, you want to be, even if it's guaranteed that they're going to connect, you want to be traveling away from them, right? So what's happening in this case, we are moving into the punch. The time of interaction is very small. So small time of interaction, there's a large force that's applied on your face to change the momentum of your face or your head, right? On the other hand, if you're traveling away, what happens is the time of contact is longer. Think of the situation where once the person's fist contacts your face, you're now traveling at the same speed that his hand is traveling, right? So let's say that now you're traveling together for 2 or 3 miles. Okay, I know that's a bit of an exaggeration, but what happens is then the time of contact is like several minutes or whatever. So similarly, even if you're just traveling away and the time of contact is what, like a whole second as opposed to like a millisecond or whatever, right, for the bulk of the impulse to be transferred, what happens is you have a larger time of interaction. Therefore, for that given change in momentum, you have a much smaller force, and so you don't get hurt as much. Here's an application of change of momentum where here's a water wheel. Water comes down and it can fall into these buckets. So here's an example of the water falling from a stream or whatever onto the bucket. The water comes down like this and sloshes into the bucket and out. And what happens is this change in momentum of the bucket applies an impulse, the pink thing, to this bucket, and the bucket tries to move down. and then the next bucket comes in place, and right, and water falls into it, and that's how you get the water wheel to rotate. And then you've got the shaft, you can attach it through gears and chains and so on to run something else that you want, like a flour mill or an electrical generator or something. Mademoiselle?
So, question. Is that what they tell
Ellie,
you?
right?
Yes.
Okay, cool.
Is that what they tell you if you see a deer in the road, like, and it doesn't move, to continue your speed, not slow down, because otherwise it's gonna like pop up on your head and hit you, you know, come through.
Oh, seriously?
So this way you're applying the most force in the less amount of time, and you should run over it versus giving less time, less force.
That's a good question. Has anyone else heard this, that if you see a deer in the road, keep going? I don't know. Look it up. See if that is correct.
So you don't run off the road.
Is that why? Oh, so you don't skid off the road or something. Like you brake hard.
Go for it, and you'll either jump out the way or...
Okay, or you hit it. Okay, so it should be okay to slow down, but don't brake really hard, so then you lose control of the car. Okay, that kind of makes sense. Extra credit to both of you. I had never heard this, but that interpretation is a hypothesis that we presented, makes sense. If you find out otherwise, let me know for extra credit, right? Okay. See, this is one of the things with teaching. I love it. I like situations and things get thrown up at me that some of the times I can figure out, some of the times, hey, wow, that's really weird. And maybe somebody has a reason. Okay. Next slide. Okay, conservation of momentum states that momentum is... Conservation of momentum states that momentum is... Is what?
Always the same.
It's always the same. Okay, extra credit to you. Okay, conservation momentum states, the law of conservation of momentum states that momentum is conserved. That's what I've been trying to draw out of you guys. It's obvious that you guys have been partying for the last 4 days too. Okay, so if there is no external net force on the object, then momentum will not change. It's basically what conservation of momentum says. So let's say you had two cars that are coming in and like they collide with each other. What happens is the total momentum of the two cars prior to the event, m multiplied by v, before the event, total momentum before the event is equal to the total momentum after the event. Right? Before the collision, after the collision, total momentum before the collision of the two cars is equal to the total momentum of the two cars after the collision. This is immediately after the collision, with no external forces applied. In reality, what happens is you collide, this law applies, but then after that friction takes over, right? Because now your cars are like skidding on the road and so forth, and friction between the rubber of your tires and the road slows the cars down. Okay, but this is what conservation of momentum states. It's conservation of momentum that causes recoil of a rifle that we talked about, right? We said that here's a rifle, the bullet is in the rifle, you pull the trigger, and what happens is the bullet travels out with a large velocity, see the big V with a small mass for the bullet. Since there's a momentum, the total momentum of the gun and the bullet before the event, before you fire it, is equal to 0, because neither of them are moving. But after you fire it, what happens is this is traveling with a certain speed. The mass of the gun is greater than the mass of the bullet. So what happens is the gun travels backwards with a small velocity rather than a large velocity. This is why when you fire a rifle, first of all, there's a recoil, right? That's why you want to brace yourself, and you don't want like a gap between the butt of the rifle and your shoulder blade or whatever, right? Particularly for the higher caliber guns. But that's also the reason why the gun does not bowl you over, traveling at the same speed as the bullet. What happens if I were to create a gun and market it saying, hey, this is like a totally light gun. This gun is so incredibly light, it'll be very easy for you to carry around, right? It's a rifle, but it'll be easy to carry around, right? You can balance it on your pinky or whatever, and use and fire and so on. It's so light, it's the same mass as your bullet. Good marketing. Do you think that's a good gun?
No.
What would happen if you were to fire such a gun?
Doesn't provide enough velocity.
The gun, when you fire it, after you fire the gun, what will happen is the gun will travel backwards at the same velocity as the bullet. So it's probably going to take your shoulder off, probably kill you. If there is only one bullet in it, that's correct. Yes, good job. If you've got 6 bullets in it, then it will travel back at 1/7. Is it 7? I'll have to check. I'll have to think about it. Whether it's 1/5 or 1/7, right? Yeah, maybe it'll be 1/5. I'm sorry.
Once you fire it down, it won't fire as much.
That's right. Oh, so it'll be 1/6. You're right. Yes. Okay, so here's another illustration where you have 2 railroad cars. One is stationary on the track, the other is traveling towards the first car at 10 meters per second. They come together and they join hands, if you will, and they start traveling together. Presuming that these trucks or these carts have exactly the same masses, what happens is the momentum of this cart will be 10 units, 10 multiplied by, let's say, 1 unit of mass. The momentum of this cart would be 0. Good job. So the momentum, extra credit, right? Mass multiplied by velocity. For velocity equals 0, the momentum is equal to 0. So the total momentum of the system is equal to 10 plus 0, which is? Okay. What is 10 plus 0? Thank you. This will have to take you all out and detox you. Get rid of all the alcohol in your system from the 4 days. Okay, so 10 units to begin with. Now, the mass that's moving is twice as much, right? Since the mass is twice as much, the velocity has to become half of that. Because the total momentum of this system is the 5 units multiplied by the 2 masses. 5 multiplied by 2, which is 10, is equal to the 10 multiplied by 1, which is 10. This is 0, right? So that's an illustration of conservation of momentum. Okay, now speaking about elastic versus inelastic collisions. You all know what elastic is, right? Think of your socks. You pull the sock, you let go, it comes back to its original shape, right? Or the elastic, whatever, if you have elastic around your waist or whatever. And what happens when you take that piece of clothing and you run it through the dryer too many times? Yep, stretches out. It loses its elasticity. So now when you pull it, it stays stretched. It doesn't come back to its original shape. So that has become inelastic, right? Non-elastic. So similarly, in an elastic collision, a collision occurs without lasting deformation or the generation of heat. So like this object, elastic is when I bend this a little bit and I let go, it comes back to the old shape, right? If I bend it really hard, what will happen is it will stay permanently bent or it will break. Once that happens, that is inelastic. So similarly, if you had 2 cars, like 2 bumper cars at a carnival or whatever, at a ride, that bump into each other and then they bounce apart, but there's no permanent deformation, no damage to the cars, you have an elastic collision. On the other hand, if you have 2 cars on a freeway hitting each other, then you have a whole bunch of damage, right? That would be an inelastic, which is basically another way of saying non-elastic collision, right? So here's a collision in which the objects become distorted, they generate heat, they possibly stick together. So here's an example of a big fish and a little fish swimming along minding its own business. Big fish comes along and says, hey, looks like dessert, opens its mouth. Now let's say that this fish is traveling at 10 meters per second to the right. This fish is stationary. This first fish, big fish, swallows the little fish. What happens to the velocity of the big fish? Slows down. Are you all agreed on that? Because the momentum of the entire system has to remain the same. So now the combined masses, right, are moving to the right. So the total combined mass is larger, which means the velocity has to drop. Good job. Okay, so this is an illustration here. Collision. Momentum of car A, right, driving to the east. Car B is traveling towards the north. So car A is traveling to the east or to the right. Momentum of B traveling north or upwards. After they collide, what happens is when the two of these collide, have you ever seen like a collision at an intersection? 2 cars, right angles to each other, what direction do they head in after the collision? A lot of times, in general, kind of diagonally, right? They're coming in like this. If they collide, like not at a glancing angle or something, they'll kind of end up traveling in that direction, assuming the masses are comparable. So in this case, you see once they collide, that they now travel kind of diagonally here. And what's happening is, this momentum vector, which is mass multiplied by velocity of car A, plus this momentum vector, mass multiplied by velocity of this car. You make this rectangle, put momentum of car A up here, momentum of car A down here, momentum of car here up here. You complete the rectangle, get the diagonal, that is the resultant vector, right? So this is the resultant combined momentum of the two cars prior to the collision and also after the collision, because of conservation of momentum, right? Because momentum is not created or destroyed. Now this is applied a lot in, okay, here's an example. A firecracker traveling along, it explodes here into two fragments. The fragments go off in two different directions. So what happens is, here's the initial momentum, mass multiplied by velocity of the firecracker or the bomb or whatever prior to the explosion. After the explosion, what happens is, here's one portion going in this direction, another going in this direction. So this momentum plus this momentum should be equal to this momentum, right? So you're probably aware of cluster bombs, stuff like that. You know what a cluster bomb is? Okay, some of you do, some of you don't, right? So one variant on a cluster bomb is basically a plane will drop one bomb, right? Let's say that you got an enemy formation or something and you need to take out a bunch of people and weaponry and so on. You drop one bomb, what happens is, in the air, that bomb explodes into multiple bombs, right? So it breaks apart into multiple bombs, which then will create a cluster. So instead of one bomb landing here and you just happen to kill one tank, let's say you want to take a whole battalion out or whatever, right? And they're all stupid enough to be clustered together. So what happens is, now you drop one bomb, it explodes above in the air, splits into like 10 bombs, right? And they all land spread out to take out a whole area, right? For whatever it's worth. So that's one variant on that. So the same thing will apply to that. Single bomb coming in, when it breaks up into the multiples, what will happen is the sum of all of these momentum of all the separate individual bombs should be equal to the initial momentum of the first bomb. It's interesting, physics has been, if you go back even like probably 2000 BC, you see indications that technology, applications of physics in warfare makes a huge difference to civilization and civilizations. That a little thing like the invention of gunpowder, for instance, completely changed the face of warfare, and so changed the face of who won what wars, what battles, changed the face of history in different parts of the world, right? And a lot of that, like archery, right? Bows and arrows, that kind of stuff, people kind of learned by trial and error. Like, for the greatest range, which way would you point your bow and arrow? Would you, if there is, would you go directly upwards? Would you go at, let's say, you want to have, let's say that there are two armies facing each other, you're trying to take each other out, you want the greatest range, right? Because you want to start taking them out before they can get to you. So you got your archers. Which way do you want them to be pointing directly at the enemy? Do you want to be, what angle would you want to be pointing at? 30 degrees, 60 degrees, 77.866 degrees, 45 degrees. Good job, right? 45 degrees, and we'll see this in a later lecture, has the greatest range. So 30 degrees has the same range as 60 degrees, like complementary angles, right? Or supplementary, I always mix those up. And so, I mean, that was an application of physics. So if you see some of these movies like Braveheart and so on, like when these armies are facing each other, you will notice that they're shooting up into the air, right? And so they, with experience, they would know what kind of an angle to go at to get the range needed to take out the bad guys. Okay, now this same concept, like you've got billiard balls that are coming in. If you have one billiard ball hitting another, then the two go off in two different directions. Or in this particular case, this is what's called a hydrogen bubble chamber, where you have like a cosmic ray or a particular particle coming in, hitting another particle, and the two of these travel off in different directions. So in a bubble chamber, you can take pictures like this. You can take pictures of a cosmic ray coming in, right? And then it hits something, and it's split into two, hit something else, split into two, hit something else, split into two. Then depending on which way these go, the angles here, as well as if you do this in a magnetic field, if these are straight lines versus curved lines, look, notice how this is traveling in a spiral, whereas these are traveling in this is in a straight line. That tells you something about the charge of the particle and tells you something about the mass of the particle. And so that's how we determine, oh yeah, that's a quark, or that's a specific baryon, or a specific hadron, or a specific dinosaur or something, right? Okay, so that ends. So just a reminder for you to go ahead and when you look over the slides, make sure that you look over the questions, the multiple choice questions associated with the lecture. That's your responsibility, right?